and she's going to continue talking about bin packing. Weina Wang is a assistant professor at CMU Computer Science, and she has won several awards, including Outstanding People Award and it's a Clean Award. And today she'll talk about stochastic bin packing.
Thank you for the introduction, and thank you for inviting me here, and thank you everyone for coming to my talk. So today I would like to talk to you about a problem where we use the stochastic bin packing formulation, but it's motivated by server utilization problems in a computing system. Okay, I don't have many slides, so I hope I can just get across the main ideas we have, and I hope they can be useful to problems you've been working on, like in some way. Okay, so let's get started. So this is, like I said, this is the stochastic bin packing formulation. So the overall setting is like this. So we have like items arrive to the system over time. And whenever an item arrives, we need to give it to a bin immediately. And in this system, we have an infinite number of bins at our disposal, okay? And each bin has a capacity M. So like indicated by the width here. And yeah, so we're going to see like how this capacity plays a role, okay? And contrary, like in Daniel's talk, he stick to the abstract formulation, but here I'm going to do the opposite. Actually, I'm going to switch to the actual application we are thinking of, okay? And talk about things in that way. So in our application, the items will be jobs, okay? So they come into the system over time, and the bins will be servers. And the capacity will be the resource capacity of each server. Think of it as like the number of CPUs each server has, okay? And now in the traditional job model, so each job will have a fixed size, fixed resource requirement. And throughout the whole time the job is in the system, it has this fixed, determined beforehand resource requirement. Okay, but I guess here, even with this traditional job model I'm thinking of here, is a little bit different from a lot of the bin packing model, because jobs could depart over time. So we assume the jobs only stay, each job only stays in the system for a random amount of time. Okay, so and then like for the arrival thing, we will also need to assume like they follow a Poisson process. So the system will be in certain steady state once you decide how to allocate jobs. Okay, so like in this setting, for example, a job comes in, we give it to the first server. Another job comes in, we give it to the first server, and then another one. And then jobs could depart. Like for example, this job, the last job here, just departed. Okay, and now another job comes in. We couldn't fit into the first server, so we will give it to the second server, and it goes on like this. Okay, and when we design this job allocation or job assignment policy, the goal is usually this. So we want to minimize the number of active servers, but the system has a steady state. So what we are actually doing is to minimize the expected number of active servers in steady state. So active just means like the server has at least one job to work on. Okay. Okay. So then, so in our work, we are going to consider. Oh, sorry, I forgot to mention. So there has been a line of work on this previous model, which has designed a series of algorithms that have asymptotic performance guarantees, optimality guarantees. Okay, I'm going to talk about the specific asymptotic regime a little bit later. Okay, and there's a vast like literature on bin packing problems, dynamic bin packing problems, but I'm going to like skip that. This is the most related line of work. Okay. Okay, so in our work, what we are considering is a new job model. So in this model, instead of having a fixed resource requirement, the resource requirement of a job could vary over time. Okay, and exactly how it varies, I'm going to specify that a little bit later. But generally, like for example, the job here, sorry, I think that job has departed, but I intention to have a job there, and over time it could expand. Okay, and once the job expands, the capacity could be violated. But we assume that we can tolerate the violation to some extent. we put a cost constraint on the resource contention. Okay, we put a budget constraint. We assume like now we are going to minimize the number of active servers subject to this cost constraint. Okay, so this is a little bit similar to the overbooking model Daniel talked about in the previous talk. So you could overuse the resource, but you need to pay certain costs. Okay. So why do we want to model the time varying thing? Why do we care about this problem? Sorry, you have no? Okay. So it's motivated by this kind of resource usage pattern in computing systems. So basically, this is like a cartoon illustration of the pattern. The main message is like this. So if you look at the peak usage, the peak requirement is much higher, but you only use the peak requirement for a very short amount of time. You don't use that many CPUs all the time. Okay, but if we allocate the resource based on the peak requirement, then that means a lot of resource we reserved for this job is going to be idle, and then like we are going to have a very low utilization on each server, and then that means we may need to have a large number of active servers. Okay, so what people actually do in real systems is they actually overcommit the resources. But that comes with a cost, which is like this possible resource contention, right? So our formulation here with the time varying job resource requirements captures this relationship between utilization and the potential cost for resource contention here. Okay. So now let me tell you a little bit more about our job model. So I said like the resource requirement is going to change over time. This is how exactly it changes over time. It's going to follow a Markov chain. Okay, so in this example, the Markov chain basically has like those two main phases. The phase L here means like the resource requirement is low. It has a low number. It requires a low number of resources. And this another phase is high, so it requires a larger number of resources. And it could transit over time according to those transition rates. And there's a special phase that denotes the completion of the job. So then like once you enter this phase, like that's absorbing phase, you're never going to leave, so the job is completed. Okay, so this is just an example, like our model, we could work with a more general Markov chain with the different phases for different amounts of resource requirements. Okay, so, and then like the jobs, so if a job is in phase L, we call it a type L job. If it's in phase H, we call it a type H job. And the initial type like is given by an initial distribution among those two phases. Okay, and this those Markov chains of different jobs, they evolve independently, and this dynamics is exogenous in the sense that like it's not affected by the resource contention. So think of each job as like a container job or like virtual machine job. It's serving as user facing. It's serving demands that come from the users. So the actual amount of resources needed is actually determined like externally by the users, and when it's going to complete is also exogenous. It's not affected by how we schedule them. Okay. So then, as I think I've mentioned this, we will assume the jobs come into the system following a Poisson process. Okay. So now I have specified like all the parameters basically of this problem. Let's think about the problem a little bit. Okay. So this is the system we are looking at. And if we look at it directly, the state will consist of like all the number of jobs of each type on every server. So we are going to have a lot of state, right? The state space is really large. So which makes it hard to optimize over, and potentially also harder to implement if we want to do an optimal policy just over like directly over the whole state space. Okay, so we have to have some way to reduce the dimensionality here, and here's a common approach, commonly used in the queuing literature. So what we are going to do is we are going to actually look at each server. We want to look at each server separately. Okay. When we look at them separately, we want to evaluate like whether a server is in the position to take a new job or not. Okay, so for example, but this is not that straightforward to do. Let's look at this case, for example. If we look at the first server, okay, it has a lot of idling capacity, right? If we give a new job there, the risk of violating the resource capacity might be low. Okay, so we might be good on that front. However, like if we don't allocate this job to server one may empty like very quickly because it only has one job in service, right? And if it empties, then we have one fewer like active servers. But if we give this job to server one, then like it will take longer to empty, so we may not be reducing the number of active servers in that sense. Okay, but for the second server, this job will fit nicely into the second server. But those jobs could expand, right? If they expand, then we violate the capacity. Then like it's hard to say like whether we really like we will be still like within our budget or not. Okay, question.
Just put the time varying model of the sequential. Does it start changing after you assign it, or?
Yeah, like when it comes in, it has an initial phase. Like you know that initially it uses this Markov resource, and it will start like evolving according to the Markov chain.
Even when it's in a queue?
There's no queue in the system, so whenever a job comes in, you need to assign it immediately, and it will start evolving.
And if you don't assign it, like you can choose not to assign it?
I will always assign it because the model is like I have an infinite number of servers. So the rationale is like so nowadays like the number of servers is usually not the bottleneck. You can always turn one more server on. Okay. Any other questions on the model?
What is the objective on how much you're allowed to violate the capacity here? Is it like
it's a pre-specified budget.
okay?
Yeah.
Is it like the expected?
Yeah, it's the expected cost. Yeah, expected cost rate actually cost rate over time.
I have a question. Like in the previous page, it seems like you are assuming the Markovian of the transition. So. Yeah, is there any like justification of the Markovian buffer?
It's not like direct. If you one justification I can have is like this. Okay, so right now it's Markovian. So it seems like, for example, if you are in this phase, the time it takes you to complete is an exponential distribution, right? But we could potentially like make multi-phases out of the same resource requirement. Then the finishing time will be like a phase type distribution, which can approximate basically many distributions, like it stands in the distribution class. So in that way, we could have made this more general, but there's some caveat to it, but like it has the potential to be generalized. Right now, it's a Markovian model.
Yeah. If the job requires more resources such that you're violating the constraint, that does not change how it evolves in this Markov chain.
Right. That's what I'm trying to justify here. I'm assuming that like we are not like this. It's not affected by that. Which maybe we can debate about it. Yeah.
What happens if some jobs in the servers expand and you violate the entire budget constraint? So if this happens,
so we want to design a policy to make sure that doesn't happen in expectation. Yeah, but temporarily it could violate the capacity. In that case, we don't kick the jobs out. We just keep it there and suffer through that period of time. Okay, so this is like when sometimes the resources is indeed overused, then the server will be in like under stress, but it will be fine if it's not too much.
If you have one server that's violated by 2 versus 2 servers each violated by 1.
Oh yeah, that's a good question. So actually, like we kind of assume on average, like if you pick a server out of other servers uniformly at random kind of thing, then like per server cost is not like violated. But that's a good question. So we didn't distinguish between the cases where one server suffers more, the other server suffers less. That would be like a more detailed model, you said, yeah. Okay, so let me keep going. Okay, so here we're saying, okay, to reduce the dimensionality of this problem, we may want to evaluate each server separately and then like give a job to them. Okay, and decide how we want to allocate the job. So basically you can think of an analogy which like this is the scheduler is a greedy manager. Okay, and those servers are the employees. And the manager really wants to hire as few employees as possible. And so the manager is trying to like overwork each employee, but each employee can only take like so much. So you cannot violate like the capacity constraint. Okay, so keep this analogy in mind. We will actually come back to it a little bit later again. Okay, so we want to evaluate each server, and like once if we take this approach, we also need to kind of relate how we evaluate each server to the actual number of active servers at the end, right? Okay, so to realize, so this is basically the approach we are going to take. To materialize it, we come up with this framework. Okay, so this framework so basically under this framework, we are going to take like all the policies in the original system, the original infinite server system, and we are going to establish a mapping between those policies and the policies for a single server system. Okay, I'm going to tell you about the single server system in the next slide, but here I want to give you a very high level overview of this approach. Okay, so the approach is like this. When we do the mapping this way, okay, we take a policy in the single server system, and we need to construct a server in the infinite server system based on that. And when we do that, we will use this single server policy sigma bar as a guideline for evaluating each server in the original system. Okay, it's going to tell us whether a server is going to be able to accept one more job or not. Okay, and then like we are going to relate the performance of sigma to the properties of sigma bar. Okay, so this is what we can do with this direction. And for the other direction, it's more for the purpose of showing optimality of the algorithm. So basically, this allows us to optimize over this policy class, like and then still guarantee that. So then like this direction of the mapping will guarantee that if we optimize here and then map it back here, we are going to get optimality in the original problem. Okay, so this direction will be more interesting, and so I will focus more on this direction in the rest of the talk. For the other direction, it's also interesting because it's the converse result. So if you are interested, we can talk more about that offline. Okay, so now I'll tell you what is this single server system. It's quite simple. It's a single server system. So it has a single server, and this server has access to an infinite supply of all kinds of jobs. Okay, and then this server can decide, okay, whether I want to have one more job of certain type or not. It can request jobs at any time. And the constraint it has is still this resource contention cost constraint. Like we have the same budget here. And while we are doing this requesting policy, the goal is to maximize the throughput of this server. So basically how many jobs you can finish per unit of time. Okay, so just as a heads up, why we want to maximize throughput, like at the end, each server here will be like a single server in the original system. So if each server is serving a lot of jobs very quickly, then we need a fewer number of servers. Okay, that's the high level idea why we want to maximize the throughput of each server. Okay. Okay, so basically the policy here is like a sigma bar here is for this single server system. Okay, so now I'm going to tell you how we what can we get from this conversion. Okay, so although we need to convert the policy this direction, but the problem specification is still for the original problem. Okay, so for the original problem, let's still take our example. Remember the job is like this, okay? And jobs arrive, like jobs of two types arrive to the system. Let's assume they have arrival rates, lambda sub L and lambda sub H. but timed by a scalar r here, okay? And what we are actually going to do is we are going to think about this asymptotic regime where r becomes large. So this is to model the situation nowadays where you have a lot of demand for your computing system. Your computing system is usually really big, okay? So for people with more TCS background, think of R as the input size of your problem. Okay, so we want to understand this problem when R is large, okay? Okay, so this is the problem specification. And then once we are given, yes, illustration, we are going to increase the rev rate along certain direction, okay? Okay, so once we are given this, now if we have a policy in the system, so we want this policy first to satisfy the budget constraint, that's for sure. But the throughput thing is like this. We consider a policy whose throughput is also along this direction, okay? It's along that direction, and the throughput, if we are given a policy, the throughput, the difference between the throughput the actual rev rate will be by a factor of n bar here. Okay, so n bar is something determined by the policy sigma bar. Okay, so what is n bar? Like I said, if a server acts as a single server in the original system, n bar is the number of copies of this single server we need to satisfy all the demand here. Okay, so actually, indeed, when we convert the policy, we show that this number n bar will be basically an upper bound on the number of active servers in the original system. However, this is asymptotic optimality, so we have a factor of r to 1 over square root of r here. Okay, just for the context, the optimal n bar will be on the order of r. So this a square root of r is a diminishing fraction of that. Okay, and the constraint we also actually violated a little bit, but it's small when r is large. Okay. Okay, so in this sense, once we can optimize over n bar, we can get asymptotically optimal policy for the original system, and that is our main result for the problem. Okay, so any questions on how we phrase the results here? Here. Yeah, Sanjay.
So I should think of the budget as a rate and not a cost.
Yes,
right?
it's actually a rate. It's a constant rate. Yeah, I didn't make that super explicit. Yeah.
What is n bar again?
So n bar, once we are given a policy sigma bar, we can compute its throughput, it has a stationary distribution, and the throughput will be a vector. And if we align this vector with the original arrival rate, they will differ by a factor. And this factor is our n bar, is determined by the policy. Okay, or you can think of this as a constraint we work with. We want to come up with the policy in sigma bar such that its throughput timed by a number is equal to this. And then we will optimize over all the policies to minimize this number. Okay, so yeah.
I know you said you won't talk much about it, but is n bar an upper bound as well on any policy for the?
It's so we can come up with if we minimize n bar, we get n star. That will be a lower bound for any policy of the number of active servers in the original system. Okay. So that's why we can guarantee optimality, because this is lower bounded by basically n star.
It's a lower bound subject to these budget constraints.
Yeah, subject to the budget constraint. And in the lower bound, the budget is actually exact, it's not violated. Okay.
Question. So still about this constraint, so is n bar two-dimensional in this example?
It's one-dimensional, it's a number.
And throughput is also a number?
Throughput is a vector, sorry. Throughput for type L jobs, throughput for type H jobs.
Okay.
Yeah. So if it's not exactly aligned, we can take the, we actually just need to make sure this throughput times the n bar is larger than or equal to the vector, so all the demand is satisfied.
Okay.
So in that sense.
I
Yeah. Okay, great. So now I'm going to finally tell you how we actually do the conversion, okay? So here's our algorithm, okay? So for any server in the original system, let's take this server for example, we're going to copy its state to a single server system. Okay, so this is a single server system, and we're going to run this policy sigma bar on this single server system. Okay, so once we run this, at some point, this server says, I want a job of type L. Okay, once it does that, we generate a token to the original server, like the server in the original system, like type L token here, we put it there. Okay, so we do this for all the servers, then we will get like different kinds of tokens attached to each server. Okay, now when the actual job comes into the system, there's a type L job that just arrived. It checks all the tokens of its type. It checks all the L tokens and picks one uniformly at random, and then we remove that token, and that job goes to that server. Okay, so yeah, let's come back to the greedy manager example. Or you can think of like the scheduler as the department head, and those servers as faculty members, or like the scheduler as your PhD advisor, and those are PhD students. Pick any example like you feel like you can relate to. Okay, so in this case, what our policy does is like this. Okay, so each employee here, they will look at their own state, okay? And there's some oracle that tells them, okay, so now it's time for you to take one more job, okay? Once you hear about this, you will put up a sign saying, okay, I want a job of type L, and I volunteer for this kind of jobs. And now like the manager, when the manager's job is simple, when the actual job comes into the system, the manager just looks at all the volunteers for this job and picks one like uniformly at random. Okay, and if there are like nobody who there are no volunteers, then the manager is forced to like ask for someone who has been inactive for a certain time, like who didn't get paid previously. Okay, so then like the payment, of course, the manager doesn't really want to do that, right? Okay. Okay, so yeah, so although like this is a really good system for the manager, maybe not like so good for the employees, but luckily here we're only overworking the servers, not like actual human. Okay, so now this is how the algorithm works. Let's think about intuitively with those tokens. How is the throughput of each single server system related to the number of active servers? Okay, yeah.
Just question. It's like I should think of each server like, what is my capacity? Like, can I get a high job or can I get a low job? And then I just communicate that.
Yeah.
So what is this? This is greedy. No, I feed it at random.
So it's not. So in what sense do you think it's
like
greedy?
a job comes? I look at all the servers that can actually take the job.
Right. But each server like thinks about its own actions really carefully. So the whether I want to take one more job or not is determined by a policy, and the potential like we want to actually optimize over the policy which satisfies the constraint but maximize the throughput.
And what does it look like, the policy?
The policy that at the end we come up with, actually like the policy we come up with, we just kind of form a linear program of the MDP problem, like a linear formulation of the state action like frequencies, and we solve that. We didn't have like a really intuitive policy at this point.
So potentially we should think of this sigma bar as, let's say, optimal policy.
Right. Yeah. Let's think about that sigma bar as the optimal policy.
Okay. So maybe just following Andreas's question, suppose the job sizes didn't change. So in just the traditional bin packing, then this would become the greedy policy. Or I think that's
that's a good point. Thank you. Cindy, you have
Yeah, the single server policy sigma bar is applied to the state of its own queue, its own capacity, or it's on the ensemble.
It's its own state. Yeah, but there's some like nuance to it. I will like we can chat more offline, but roughly speaking, it's its own state. Okay.
You're like
Okay. So it's like, so the probability that I change my size, is it like, does it Does it depend on the problem parameter, on the number of jobs, for example?
No,
Or
no.
the rate?
Yeah,
No.
it's
So
actually exogenous. Like it's controlled by something external. Yeah, so that may
Does it
not be
change-
the best assumption. I
Does it
agree.
change completely the problem?
I think it will depend, like it depends on how much it depends on the actions here. Like if we think about the
Because I was thinking that like, okay, now you do but if I want to describe an optimal policy, I would say that like if there are many jobs, there is a high probability that some of them will become big, right?
Mhm.
But it's
But
also
that depends on that depends on the relative relation between like the expanding probability and the leaving probability. If you have a lot of jobs, it could also be like you have a large chance that someone will depart like within. It depends on like how relative those rates are.
yes.
Yeah.
So the single server problem is not strictly speaking satisfied because of the assignments that students are
So yeah, so the yeah, so it's a little bit complicated, like how they depend on each other, right? Like if you just look at this single server policy, yeah, it will depend on if the state here changes, the state you will need to also put in the new state for the single server policy. So the single server policy here is not a system independent system its own, right? But at the end, when we prove it, like we only couple the dynamics of those systems. So we don't really follow along, we don't really think through the whole sample path of the single server system.
So based on what you've described so far, this policy conversion from single server to infinite server has purely black box access to the single server.
Right. Yeah, we need to make some assumptions it's kind of at least right now how for the proof to work, we need this policy to be kind of Markovian. It will request jobs based on the current state, not the history, but yeah.
You don't need to open it up to surgery. Or
No.
anything.
No, we don't need to look into the policy. That's right. Yeah, at least the conversion part. Like if we just want to run this algorithm, it doesn't depend on anything inside of the single server policy. Okay, so let's just get a little bit more intuition for why the throughput is related to the number of active servers. So basically, if each single server has a high throughput, then this is someone who is really efficient at processing things, right? So then then it's good, it's kind of you have volunteers all the time. Even if you just have a few number of servers here, they can satisfy the demand. Okay, so higher throughput will imply a lower number of active servers because you have tokens available from them all the time. Okay, so to make the policy more well behaved, we need to add some more details to the conversion part. Okay, so so here we add two things. So first, we only, I guess this may be related to your question, but let me first say what this is. So we can run the policy. We run the single server policy for only part of the servers, specifically for only n bar of the servers. Intuitively, we only need n bar copies of them. So then at the end, we will show that the number of active servers is basically upper bounded by n bar. So we don't care about the servers outside of n bar. Okay, so n bar does depend on the policy, although we don't need to look into the policy per se. Okay, it depends on parameters of the policy. Okay, yeah, so this is one part. Okay, we cut it here. And another thing is we want to regulate the number of tokens we have in the system. So if the number of tokens is too large, is larger than square root of r, we remove a token and we put a virtual job inside. And then the virtual job will work like a real job. It evolves over time. Okay. And at the end, we will show that the number of virtual jobs is also not too much. It's on the order of the square root of r across the system. Okay. Okay. And okay, so those are the fixes we do for the system to be more well behaved.
Why do you care about saying anything about the expected number of virtual jobs?
So yeah, let me explain that depends on that's related to the nuance of running this single server policy. So when we run the single server policy, actually I lied a little bit. We didn't just take the real jobs as its state. Okay, we actually take the real jobs plus virtual jobs as its state. So for them to work similar to each other, we need to say, okay, the number of virtual jobs doesn't affect that much. Yeah. Okay. Okay, good. So now I'm going to show you the first key idea in our analysis. So the first key idea in our analysis is basically what I have been telling you. Like we want to show that each server here is like in the sense is close to an actual like a single server system. Okay, so we want to show that they are close to each other. Okay. However, if we think about of course, if like for the single server system, it generates a request. If the request can be immediately replaced by real jobs, they are exactly the same, right? Like that would be just great. But how the actual system works is like this: we generate a request, the actual server generates a token, and then you need to wait for the job to come and picks your token to realize it. And then like we also have this regulation for the number of tokens. They may overflow and we need to realize them using like virtual jobs. So it has all sorts of those complications. And because of that, the servers are actually correlated together, right? When the job comes in, you need to look at the tokens of all the servers. So they are correlated, and that's causing us some like a difficulty here. Okay, what we ideally want to show is like each server will look like an independent copy of the single server system. Okay, so the main idea we come up with is actually very simple. Okay, so what we do is when we look at the single server, when we look at each server in the original system, we look at this number ki tilde. That's for type I jobs. Okay, it's the number of actual jobs plus the number of virtual jobs plus the number of tokens. Okay, so can you see how this like just a simple trick can decouple the servers in the original system? Like why when we consider the sum, it's all good. Let's think about the case when the job arrives. Okay, if a job arrives to the original system, what does it do? It replaces a token with the actual job on the server, right? In other words, it doesn't change the sum of the number of jobs and the number of tokens on each server. Okay, so that part is taken care of. And let's think about the token overflow. When the number of tokens is large, what do? We replace them using virtual jobs. Okay, so then like in other words, the sum between the virtual jobs and the number of tokens doesn't change like again. Okay, so basically if we think about the sum, that kind of decouples the servers in the original system, and that is like makes the proof like go through. Okay, and now let's yeah, that is my question. I forgot to show this question. Okay, so and the arrivals and token flows do not really affect this k tilde. And now let's compare this with the k bar, which is the number of type I jobs in the single server system. And we want to show they are close, right? So one thing we need to, what I described is the kind of the arrival parts of the dynamics. There are some other parts where, for example, like a request to the single server system, and that will generate a job here and generate a token here. So it changes them like in a similar way. But like I said, the state will differ by the number of tokens, but we will bound the number of tokens at the end. Okay, and another thing is this job departure process, and that will differ by the phase transition. If we compare this with this, also like if we want to make sure this is similar to this, then like they differ by the number of tokens which we will bound. Like the number of tokens is actually bounded. Okay, because the way we implement the algorithm, we force the number of tokens to be bounded. Okay, and okay, so now we can basically show all the dynamics are similar to each other between those two systems, and we use a technique called the Stein's method to actually show that in steady state the distribution of them are similar to each other. Basically, if their their transition probability, transition rates are similar for the two Markov processes, then you can show that their stationary distributions are also close to each other. Okay.
This particular lemma being like system. So far from what you said, doesn't seem to depend on there being two types.
Right. Like I said, all the results come through when you have multiple types. Like that's just an example to help us think. Yeah. Okay, so this is the part we show they are similar to each other, and then we need to take care of the loose ends like the virtual jobs, and also so we need to take care of the virtual jobs part. And there's another part which is like we said, we only run the single server policy for the first n bar servers. Let's call all the rest the backup servers. So there will be jobs that go to the backup servers, and we will show that that part, like that number is also small. So basically the number of virtual jobs is small, the number of active backup servers is also small. Okay, so and interestingly, those two things can actually also be shown at the same time. Okay, so to see that, let's think about this dynamics for each type of tokens across the whole system. Okay, so we have like, let's think about the type L tokens, and we said we basically force it to be within square root of R, right? Okay, so then when is the number of tokens increase? When is it going to increase? Okay, it's going to increase if the single server system says we want more type L job, right? That's when we generate a token. So it will increase if a server requests type L jobs. Okay, and when does it decrease? When does the number of tokens decrease? It decreases if there's a job arrival of type L and it replaces the token with the job, right? So it decreases like this. Okay, so basically the number of tokens here is doing a random walk from 0 to square root of R. Okay, and then let's think what happens if the number of tokens hits this boundary here, square root of R. What will we generate? Virtual jobs, right? So we will generate virtual jobs. And what will happen if it hits the other boundary? We run out of tokens. What do we do now if a job comes in? We send it to a backup server. We turn on backup server, right? So this is when we generate a job to the backup server. Okay. Okay. So then by looking at this random walk, we can actually get those two things at the same time. So basically, this is more or less a balanced random walk. Okay, the rate to the left and the rate to the right is like they're roughly equal. Okay, so then like in steady state, basically this will be a uniform distribution from 0 to square root of R. Okay, so the probability for being at state 0 and being at state square root of R, they are the same. They are 1 over square root of R. Okay, and now like think about the rate of generating virtual jobs, which is basically the same as the rate of sending jobs to backup servers. That will be the arrival rate divided by square root of R, and it will be on the order of square root of R. Okay, so that's the intuition for like why we only have this number of virtual jobs and the backup servers. Okay, so once we take care of that, we basically shows that the number of real jobs on each server is similar to the number of jobs in a single server system. Their distributions are close to each other. From there, we can argue the cost will be similar. And we can also argue like the number of active servers will be close to the n bar n bar that's determined by the single server policy. Okay. Okay. So yeah, basically that's like that's the whole thing I have. And to summarize, we consider this problem of analyzing jobs to servers where the jobs have time varying resource requirements. We have this like asymptotic optimal policy, and more interestingly, we have this conversion framework that allows us to convert between the original system and the single server system. And one part, like I highlighted in the talk, is one direction of the conversion, and we call this our meta algorithm. Join the recently requesting server, and it actually works for any policy here, even if your policy is like suboptimal, right? So it gives you a performance guarantee. Okay. Okay. So yeah, that's all. Any more questions?
Go ahead.
About the Markovian assumption, so you're going to say that, I guess the last part of the argument would be that the two Markov chains with and without tokens is similar, and so.
Yeah, so it is actually, yeah, maybe let me be a little bit exact here, sorry. Okay, yeah, what we actually show here is like this K tilde thing is close to the number of actual jobs. So this K tilde includes the number of tokens at this step.
But coming back to my previous question, it's not really a Markov chain because of the external.
Yeah, I think this here, I'm just illustrating this intuition. So we are not actually thinking of the actual sample path, like how it works, like every step for this single server system, because like you said, it will depend on like things happening here. It's not the actual Markov chain. So what we actually do is just like take this, the generator of this Markov chain and compare it with the dynamics of this number.
Basic of the
yeah. Right, we need to bound their difference like in different ways. We solve a so-called Poisson equation like that can translate between the difference in the generators to the difference in the distribution.
Two questions. So one is, why not consider assigning this higher probability to servers which have tokens of some type if a token comes in? Have you thought about that? That could.
So you mean
maybe
the probability?
It has a minor effect on it, but I don't know.
You mean like the probability depends on the number of tokens, or it depends on when the tokens are generated? The number. Okay, yeah. So we pick like the tokens uniformly at random. If a server has more tokens, it will be picked like with a higher probability.
Oh, because it's like you're counting the server multiple times.
Right. We just
all right,
count
so
the
it's
tokens.
just proportional to the number of tokens.
Right.
Associated with the server.
Right.
Good. The other question that I had is that it seems that it's a pretty key assumption, although maybe you have this general deduction that you have this underlying Markov chain model.
For the
So
job.
what? Yeah, for the job. So what do you do if you don't? What would you do?
Yeah, like if you don't know the parameters of the.
Right.
Yeah, right.
Or like, yeah.
Yeah, that's actually something I'm thinking about, because our conversion, like Valu pointed out, doesn't really depend on how the single server policy works.
Right.
Okay, so if you have a certain way to like train the single server policy, like do it while learning like the characterization of the jobs, like you can do whatever you want to solve the RL for that single server problem. Then we can convert it to a multi-server, to the policy in the infinite server system. So that will be kind of an advantage of the conversion. But as to how to solve that single server problem, right now it does require the knowledge of the Markov chains, but perhaps that part can be taken care of like by getting some data where you can learn the distributions of the jobs, or you can get some predictions for the jobs that tells you how they are going to evolve, things like that.
So if you have an approximately optimal policy for the single server problem, the approximation error.
So what we show is like, let me just go back here. Okay, so here this one is not necessarily the optimal policy. As long as you calculate this n bar, we can convert it like with this guarantee.
Okay.
Yeah.
Basically, find the smallest n bar where twice the throughput times the n bar is bigger than
Right.
that vector.
Yeah.
And then plug it in here.
Yeah.
You get this further expansion.
And if there is some approximation to the optimal value of m bar, say m bar star is the optimal smallest number we can achieve, then there is an epsilon gap from optimality, then we just have
Yeah, tell me it's like co-author for the paper. Yeah.
So actually, I guess as a follow-up to Sabaz, I was thinking it feels like your token system should be able to handle something like a general restless bandit. Like you just need to be able to solve a single node problem, and then the way you pick the nodes, you're kind of saying the token takes the role of an index policy. I mean, I think that would be, it's a really cool policy. Like if you can, it feels like it should
Like for each single part, we don't really assume the full knowledge of
Yeah.
the statistics. Yeah. I think that would be super interesting.
But one quick thing about the virtual jobs.
Mhm.
So another natural thing to do would be to put a reflection at a certain point at like square root r for the random walk, and just say, I don't really need to generate a virtual job. I just don't do anything.
Yeah.
And show that this is stochastically dominating the system with the virtual job. Like instead of doing a generator coupling, say it's sort of just a dominance in.
Oh, yeah, that's a possibility, right? Yeah, but I on the high level, I would argue like how we deal with the number of tokens, how we deal with the backup servers. Those are more like for the proof techniques. If you don't have any of those, I think the algorithm will work fine. Okay, thank you everyone again for listening to my talk.
That's really nice.